Okay, so this quick video here is going to show us how to simulate active filter and get the magnitude versus frequency plot here. So I'm going to just first off pick out just an LM741 component out of the op amp directory. And I'm going to pick out just a single resistor from our analog, and then a single capacitor from the analog library. Now, the cutoff frequency for these, and I'm leaving this here where that says plus and minus. It's important to notice where the plus and minus are on your op amp. I'm going to go ahead and quickly just compute here. I'm going to maybe change this. Let's change this to 10 nanofarads and leave that at 1K. So let's compute where that cutoff frequency would be. So this would be a cutoff frequency of 31.8 kilohertz is what I get when I do my computations using my calculator here online. So we're going to finish building the circuit here. So I'm going to need a couple other things. I'm going to need, a ground, 0 cap sim. Put another one over here. I'm going to put one down here. I'm going to need some power supplies because in order for an op amp to work, we need some power to it. And then I'm also going to need an AC signal, VAC source. And maybe I'll put in one more ground here, just so I like having fewer wires. Now I'm going to connect things up here. And now I'm looping the output terminal back to the input terminal here because this is going to be a unity gain active filter. If we put resistors in here, remember that would give us gain as an active filter. And then what's the last thing here that I want here? Oh, I know what I'm doing. I need some power supplies. So, and I'm going to put in one more resistor here. This resistor isn't part of the circuit as far as determining the frequency or anything like that, but sometimes it's useful to have a load here, and I'll make it relatively large, 100K. Sometimes it's useful to have a load there for simulation purposes so that there's something for the output voltage to drop across so that we can actually get an output. Sometimes you don't get a good solid output from a simulation if you don't have that there. Now I need to get power to that op amp. So I like using these VCC bars. And I'm going to put 2 down here to start with. And I'm going to rename this one to V positive. And I'm going to rename this one to V negative. And then I'm going to copy and paste that to my positive one. Copy and paste this to the negative side, and then rotate that, and then I'll go ahead and connect those up to the op amp, and then I will also connect these up as well. And we also need to make sure we put power here. So I'm going to just go ahead and do 12 and negative 12 volts. That's a pretty standard voltage to use on a 741 op amp. We're not so much concerned about the voltage we're using because we're going to be doing an AC sweep here. This is my low-pass filter here. That's an active filter. All right. So I'm going to do a new simulation profile here, and I'm just going to say AC sweep. I'm going to call it, and then it opens up here, and I'm going to go to AC sweep. You want to make sure this is logarithmic. I'm going to start at 1 hertz, and I'm going to go ahead and end at 10 megahertz. So you want to do 10, and then you need to type in meg. If you just do capital M, it won't recognize that. And then I'm going to do 50 points per decade, and then hit OK on that. And then I'm going to go ahead and run my simulation. So my simulation doesn't show anything right here because I haven't plotted anything. Because I like to run the simulation first, because then I can go to Pspice Markers, Advanced dB of magnitude. So I can look at the decibel of the magnitude there. And we can see here that we get this kind of low pass behavior here going on, where it's flat, 0 dB, and then it starts tailing off here. And let me make this a little bit thicker, because you might not even be able to see that on the screen here. So let me change the color, make that a little bit thicker. So you can see here it's got this nice little tail off going, and you might say, wait, it's going off really far, you know, at the 1 megahertz range, and you know that has stuff to also do with the op amp, is why you're getting this straight cut down here as opposed to it continuing on like a straight line here. So there's more going on than just the components here as far as the resistor and capacitor. But let's go ahead and use our tools here. So I'm going to go to Tools, Evaluate Measurement, and then I'm going to just do my cutoff for my low pass. Actually, before I do that, I'm going to go back here, rerun my simulation, because I'm going to go ahead and label this node here as an output. That's just going to make it easier for me to actually do my computation. So redoes simulation. Let me again make that line thicker. Okay, now we're going to go to Trace, Evaluate Measurement, and we're going to do Cutoff, Low Pass, and then I'm going to turn off the cold currents, and then we should be able to see V output. That's what I want. And then we get 15.878 kilohertz. And we computed 31.8 kilohertz. And you might say, well, what's going on here? Is there something wrong? No, there's nothing going wrong with our equations here. A lot of it has to do with the op amp itself, and that computations make some assumptions here. Again, some of the assumptions we're making is that, you know, this is infinite impedance, which, I mean, it's okay for that, but that also the current going into the things are 0. So there's assumptions were being made. So you might say, I'm not getting anything close to it, but honestly, that's a pretty typical result with a 741 op amp. We could try a different op amp and see if we get a different result here, which maybe we'll do at the end of the video. But before we do that, I want to go back here and show one additional thing here. So let's say I'm wanting to simulate, but now I want to have gain in this op amp. So I'm going to have 2 resistors here. And let me try and remember, that's not the way I want to draw them. I'm trying to remember this here. This isn't the way I want to have them drawn here, so just a second. I'm going to have this one rotated. This one rotated like this. And then have a feedback resistors that look like this. Then I'll put in another ground here for it. And then I'll go ahead and make this 2 kilo ohms. So I'm now going to re-simulate this. Oh, it doesn't like that because I made that connection wrong here. Delete that, connected it wrong there. It should be connected in the output. So let's resimulate this again. Okay, and so we can see we get another low-pass amplifier, and we get a nice little bit straighter tail off here. Some of that's though because we're doing gain here now, because look here, this flat portion is not at minus 0 dB, or minus 0, it's not at 0 dB. I'm going to again make this trace a little bit thicker. But I can still toggle my, let's evaluate measurements. Let me toggle my measurements since I've already done it once. And I still get the same cutoff frequency. And that shouldn't be surprising because I haven't changed anything as far as the filter design goes, which is important because you don't want your gain to be affecting your cutoff frequency because that would make life very challenging for us. But let's say here, what should we be getting here? Well, I set it up to have roughly a gain of 3. So you'd have 3 log times 20. So it should be roughly 9.5 decibels. And you can see that's precisely what we're getting because this is 20 decibels, this is 0, so this would be 10 decibels here. So we're getting about 9.5 because again it's been made thicker here. And so though the key thing here is I'm wanting to point out is that minus 3 dB that it's computing, which is still correct, it's still your cutoff frequency, it's still half power at 15.85 kilohertz. It's not literally at minus 3 dB because in this case the minus 3 dB point would be at roughly 6.5 decibels because that's 3 dB down from the maximum decibels. Okay? So as the last thing here, let's just go ahead and put a different op amp here and see what happens if we put a different op amp in there. Let's do a TL072. Put that op amp in here and see what happens. I don't know, we might get the exact same result, we'll see. This is a different op amp, and so I'm now going to rerun the simulation. Okay, and get a similar kind of curve there. Oh, I know what's going on. We have the exact right cutoff frequency. You guys who are watching this video may have already noticed this. I made a, yeah, we get 15.857. When I had my calculator up here and computing it back in the day here, I forgot the formula. The formula here, let me type it in the text box here. The formula for computing your frequency is, of course, 1 divided by 2 pi times R times C, where those are the input. What did I do? I did instead, when I did my calculation there, what did I do? I did 1 divided by pi RC for my computation, which is off by a factor of 2, which is exactly what we should, because if I take 31,830 and divide that by 2, I get 15,915. So if I get 15,915, yeah, that's almost exactly what we're getting when we do the simulation. And that error absolutely makes sense, that we're just not taking into account other things like the op amp behavior. So hopefully this quick little video helps you simulate active filters.